Swayam Prabha. Digital India. Educated India.
It's my honor to introduce Professor Balaji from the Department of Mathematics, IIT Madras. He is a distinguished academic known for his deep insights and contributions to the field of mathematics. His passion for teaching and research has inspired countless students. We are truly privileged to have him today.
Yeah, thank you. It's a it is a great pleasure, and also it's a great honor to always be here. I have been here with the RSIC right from the beginning in 2009, and you see the so it's about 15 years, and you see one of the main things about RSIC is that we need a lot of people applying science. We produce a lot of engineers and doctors. Okay, but the important thing is that the demand is more for these engineers and doctors, and also scientists, to apply things to real life situations and try to solve problems that the world is facing, humanity is facing at the moment. Okay, so the idea was that this RSIC should encourage students to have this scientific perspective. That they should. It's not that you are let us say you have a one unidirectional approach that you want to only be a doctor or you want to only be an engineer. But now everything has got mixed. Everything is now interdisciplinary. Okay, and we have realized that everything is connected. Okay, so you have biomathematics. You have you are using DNA for coding. Okay, theory, and so many things are there. So there is you must get this viewpoint that all areas of science and life, they are all interconnected. In fact, even with art, humanities, finance, economics, psychology, everything under the sun. Okay, so you should have this wide kind of feeling. Normally what happens is that when you study in school, you see, you learn mathematics, you learn physics, you learn chemistry separately. Okay, and well, it is done like that because they have to give you the structure of that particular subject. But then the problem is that that itself takes away almost all of the time. You never know what's happening, what is the interaction. So you should, unless you get the interaction between all these things, you don't you don't appreciate. Okay, and you think that these are all singular things by themselves, but it's not like that. So one of the things that I'm going to talk about today is is about differential equations and why we should study the differential equations. That's going to be the first topic. Then I want to say something about the geometry of differential equations. And as I told you, this will also give an introduction to a couple of projects that I have put up, and of course these projects are kind of very loose-ended. Your imagination is also invited. If you want to bring in something that you know of and you want to see how it works or study about it or put it to work, that is also welcome. Okay, so I am just giving you a start. So you see, so we begin with this this question: why should we study differential equations? Okay, so the first thing is somehow that if you look at it, you could say in some sense that the source of all science is going to be nature. So oops, let me get this. It's nature. Okay, and one could say this quite safely, and the idea is that nature is you perceive, and we are we are endowed with the sixth sense. Okay, so we have intelligence. okay, and the other animals have only 5 senses, but still they are also perceiving, but probably they are not, at least as far as we know, to our extent, they are not, processing what they perceive in an intelligent way. Okay, so you perceive nature, and then you want to study. So what you want to study is, of course, when you perceive nature, you want to study natural phenomena. And of course, this includes many things. It may include a very simple thing, simple observations. You take a cycle, you sit on a cycle and don't pedal, you fall off. Okay, whereas you pedal it even slowly, then you're able to maintain balance. And why is this happening? Okay, and of course, even more subtler things, such as why did the apple fall? Okay. So the point about science is that you see something that happens, and the important thing is you question why it's happening. The question is, there is a why there, and once then the related things are how. Okay, and see, this why is something happening is at least to start to find out some reason for something that is happening, and how is trying to go deeper into it and to explain the whatever the process that is involved. All right, so the nice thing about natural phenomena is that what is happening is that you are looking at, when you look at nature, the most fundamental thing that strikes you is there are laws of nature. So the natural phenomena have, there are laws. There are nature's laws, and you see these laws. You can kind of there are many of them. Okay, there's, for example, you have gravity. Okay, and it's a phenomenon. If I drop this, it falls down, and I don't want to do that. Otherwise, I won't be able to use it. Okay, so it can do harm, right? That things fall down. They are attracted by the earth. So there's gravitation. Okay, and then there are many other things. There are natural phenomena, which, mind you, when I say natural phenomena, there are many. There are things going on in a biological sense. There are things that are going on in the sense of there's a lot of chemistry going on. There's a lot of biology going on. Okay, there's a lot of math going on. Okay, lots of things are happening. Okay, but the point is that all of these seem to follow certain laws. Okay, and the idea is that you want to study these laws. Okay, now when you want to study these laws, each of these laws, the way they are given is that what is happening is that you're observing something. Okay, now it's not enough if you observe, you must also measure. Okay, so this is the transition from observation to measurement to the theory. Okay, and so there is this thing, there is observation, and then there is measurement, and then there is the theory for that. And see, in the observation, basically you observe that something is happening. So when you observe something is happening, then there are you would like to see what the so let me talk in a mathematical sense. Whatever you're observing, you want to see what are the variables involved. So the observation is that basically what changes, and what changes, these are the variables. Okay, so for example, if you drop a stone, then the height of the stone from the ground changes, it reduces. Okay, and if you drop it from rest, then its velocity starts increasing, right? And then you can realize that therefore there is an acceleration. That is exactly the acceleration due to gravity. Okay, so you see, you have this there is the height, which is displacement from the ground. Then there is the rate at which this height is dropping, that's your velocity. And then of course there's second rate of change, which is the acceleration. Okay, so more or less what happens is that there are many variables, and you measure these variables, and here is the interesting thing. You can, when you do this measurement, here is where experiments come in. So you can do experiments and measure what is happening to various variables that are connected with a physical phenomenon. All right. So if you take the simple case of an object falling down, you can measure its height, you can measure its velocity, you can measure its acceleration, and then what happens is that you do several measurements, and then you find that acceleration is constant, right? And it has got nothing to do with the mass of the stone. You take a lighter stone, you take a heavier stone, and you do the experiment, you get the same value. So you conclude that any object is attracted towards the earth vertically downward with an acceleration. It's a constant acceleration. That is the acceleration due to gravity. Okay, so g is equal to 9.8 meter per second squared, right? That's what you normally take. So there is, you do experiments, and then you get these laws. You get these. So here is a very, very interesting thing. So I jump to that statement. So what changes is the variables. Okay. Now, how are these variables interconnected? You are measuring several variables. Now, here is the important thing. You observe that something changes. That's a physical phenomenon. What changes is, these are the variables. There are certain variables that are changing. You measure them, and then you look at the relationship between these variables that you measure. And what that comes up, that relationship gives you a law. That's how. So you see, the relation between variables, these are essentially the laws. Okay. So for example, if you drop a stone, you measure its displacement, you measure its velocity, you measure its acceleration. Then the law is essentially that, irrespective of the mass of the stone, okay, the acceleration is the same. Okay, so that is a law. So this is the simplest case of gravitation. All right. So you get laws. Okay. Now here is the very, very interesting thing where differential equations come into play. So what happens is, the laws which give relations between variables, they are actually not relations between the variables themselves, but they are actually with respect to rates of changes of the variables. So actually, so here is where calculus comes in, and what it says is, many variables are not directly related. They are not directly related in the law, but their derivatives are. Okay. So for example, so one standard law that you always study is Newton's second law. So what is Newton's second law? Okay. Yeah. So So what is the law? It is the rate of change of momentum. Okay. So d by dt of p is directly proportional to the external force. Okay. So basically, what is happening is, there's a particle. Let's take there's a body. A force is acting on that, and the force produces a change in displacement, and the change in displacement produces also a velocity. At the velocity at every instant gives a momentum, because momentum is just mass times velocity, and the momentum is changing, and the rate of change of the momentum is directly proportional to the external force that is applied. All right, this is your Newton's law. Basically, you write it as, if P is mv, so this P here is m. P is m. I think you use v. Okay. So basically, what you get is d. M dv by dt is equal to f into some, if you want k constant, but you can make the constant 1. Okay. Plus So what is it that you are going to use? So you are using m into v squared, is it? Or you want to use kinetic energy, or what is it that you want? Pardon me.
He's telling mass might change over time, right? So you get m dv by dt plus dn.
M. No. Okay. So I understand your confusion. P is mb. Okay, I am assuming that there is a object of fixed mass. I am assuming that there is an object of fixed mass, which, in fact, even take it as point mass. Okay, and you are assuming that a force is applied on it, and then you are calculating the momentum. Okay, and so v is already ds by dt, where s is the displacement. Okay, and so here and of course you take k equal to 1, basically you write f equal to ma. That's what you do. All right, you can also write this in terms of half mv squared, which is kinetic energy, if you want. Okay, and if it is involved, you can write this also in terms of potential energy if the gravitation is involved, and you can use the law of conservation of energy. Okay, so there are many things you can do, but I want to say the following thing. Here, look at what is happening here. Here you see so you see here is where what happens is functions enter. Okay, what are the functions? You have s is a function of time, this is displacement. Then you have v is also a function of time, it is actually ds by dt. Okay, and a acceleration is also a function of time, and this is going to be d squared s by dt squared, and that is going to be dv by dt. Right, and look at this law. Look at Newton's law. What it is saying is that the external force is actually related to the second rate of change of displacement, or the first rate of change of velocity, assuming of course m is constant. Okay, so moral of the story is, therefore, you see, this is Newton's law. Look at Newton's law. What is happening is the function involved is actually displacement. But does displacement figure here directly? No. What figures here is the second rate of change of displacement, which is the acceleration. So here is the point about laws. All natural laws, they link certain variables together in a relationship, and many of the variables are not exactly the variables themselves, but their rates of change. Therefore, the moral of the story is the following. All natural laws are essentially differential equations. So why should you study differential equations? Studying a differential equation is studying a natural law. Okay. Now, this is inspiration from nature, but then there can also be artificial laws, in the sense that you can make such laws theoretically. By having a theory, you can make a law. Okay, and then what you have to do is that you have to do experiments and you have to do the observation. So basically, what you have to do, you have to reverse this process. You start with the theory. Okay, based on the theory, you do some experiments and you do some measurements. Okay, the theory, you start with the theory, so that means you postulate a law. You postulate a law, that means you postulate a differential equation. And then you make measurements and you do observations and verify that your law is holding. Okay, so you see there is a two-way movement. See, going from the observation side to the measurement side to the theory is the usual, what is called as experimental science. Going from the theory back down to experiments and observation is the theoretical science, and these two have to be correlated. You have to correlate. Okay, and this is very, very important. And you see, let me warn you, you should take it probably with a pinch of salt, I should say, that the theories are you have some theory. The theory gives you some solutions. You do experiments, everything is nice, but everything is not nice. Okay, so the truth is that you take any theory, there's always a chink in the theory. Okay, so that's why science is endless. So you take what is the most abundant element in the universe? Hydrogen. Okay, and what is the easiest? So it's spectrum. Okay, the hydrogen spectrum can be explained. You have studied Rutherford model, Bohr model, then you have, Paschen series, Lyman series, so many other fund series and so on, Z-Man effect and so many other things are there. Okay, so many are there. But it's still a mystery. Just the simplest atom, the simplest element, the most abundant element in the universe. Okay, it's fine spectrum. The fine spectrum of hydrogen, you don't have a theory. There are many lines in the fine spectrum which are not explained. Okay. So the point is that people have applied relativity, quantum mechanics, they've applied everything under the sun. Okay. And they have still not been able to explain the fine structure of hydrogen. So what I'm trying to tell you is that where we know a lot of things, but where we don't know, we are absolutely blind. Okay. So there are things like this. Similarly, this is at the cosmic level. If you take now there are black holes, nobody knows where they came from or how they behave because you can't observe them. Okay, even light cannot pass through them, so there's no information. Then where did these guys suddenly come from? Okay, then people have discovered that much of the energy in the universe is dark. Okay, there's dark energy. Much of the matter in the universe is dark. Okay, and nobody knows where these things are. Okay, so you see, if you really look at it, we know only a few percent of what's happening in the universe. More than 90% of it we don't know. There is no theory. So you see, therefore theory is important. So that's why people are trying to put forth theories to explain things that you cannot directly see. So both approaches. You go from observation to experiment to theory, or you go from theory to experiments to observation. Both ways you have to do this. Okay, so that's how the synthesis is. But the moral of the story is, why study differential equations? Because this is the form in which laws exist. Differential equations are just laws. All laws of nature are differential equations. Okay, so let me write that down because it's a very, very important thing. All laws are differential equations. You have a question? Yes, please. You want a mic? No. You want a mic? You just pass the mic.
Yeah. So about dp by dt is equal to f, sir. Actually, someone asked me a question saying, what if we cross multiply dt? So dp is equal to f dt, and what if we integrate both sides? So how do we get f is equal to ma out of that? Is it possible, sir?
So I'm coming to that in the sense that, see, f equal to ma involves a, which is the derivative. What you're trying to do is you're trying to get rid of the derivative.
Yes.
In a sense, what you're trying to do is you're trying to solve a differential equation.
Yes.
So that's what I'm going to do.
Yes.
Very good. So you see, I was in fact coming to that next. So that's a nice observation. So you see, all laws are differential equations. Now, so you have these laws. Assume that you can get these laws by observation, experiment, by some theory. Okay. Then the question is, okay, fine, we have got it. What next? Okay. You have a question.
When people base theories out on something, they need to have observed something or got the motivation from somewhere. Like you can't.
Just hold the mic a little away from you.
You can't like.
Yeah. So I have been here for almost about 20 years, and I have been telling all these. I always tell all my engineering students that, see, whenever I take a class, there is this resonance. Okay, this interference. I said, with all your high tech, find one circuit or do something. This should not eat my head, but nobody has done it. Okay. No, I think go ahead.
So how do you like? So it doesn't follow the exact reverse process, right? There should be observation, theorization, and then experimentation.
No,
I'm not getting that part.
Okay. I'll try to tell you what. So you see, there is a physical phenomenon. take a physical phenomenon that you can observe. Take a physical phenomenon that you can observe. Once you can observe it, there are going to be observables, which are the variables. You observe these variables, and then you have methods of physics by which you can measure these variables. All right, you measure these variables, and then you search for an empirical relation between these variables. You get a law, right? And so that's how you get a law. And then you now say that what is this theory? This theory is, to put that law on a solid footing. See, if for example, if I take a piece of string and give a kink, then it starts traveling like a wave. All right, you have stationary waves. You drop a stone in the middle of a pond, you have these waves going there, and if this is a well, they get reflected back. Okay, all these things happen. Now you see, the point is that just seeing these things is not enough. You want a pakka mathematical theory based on which you can derive this, okay, from more basic laws. See, the idea is every law is probably has at its base a more basic law. So I am going to give you a couple of examples. Hopefully I will try to tell you how the wave equation comes up, okay, from mechanics. And I'll also tell you how the heat equation, the Fourier, comes up from the Fourier heat law, which is essentially coming from the second law of thermodynamics. Okay, so how the heat equation comes. Okay, so the point is that there are more and more basic laws from which you can derive these expressions. Unless you have a derivation for this expression, you're not sure. You only have an empirical relation. So there is need for a pakka formula. You understand? So that is how you go to the theory. This is for something that you can observe. Now suppose I cannot observe something. See, for example, there is a black hole. What is the problem with the black hole? You see, the heat, any information that goes beyond the event horizon cannot be retrieved. You cannot get any information at all. So what is happening inside is a complete black box. You don't know what's happening. Now, how do you approach this? How do you study something that you cannot see?
By studying its effects on this.
No, nearby you know many things. See, nearby I know there is an accretion disk. I know there are so many things going on. Okay, I know a lot of things. See, as you go closer and closer to the limit, which is the event horizon, okay, there is a certain limit beyond which you cannot do anything. Up to that point, you can write things. But beyond that, you don't know what's happening. You don't even know how these crazy things were formed. Okay, they've discovered a black hole moving at a terrific speed, silently in a galaxy. It's moving at terrific speed. And the size of the black hole is, I think, 1,000,000 times the size of our sun. Okay, so you can imagine such a huge giant object moving at some, I think, almost you can check the exact information, almost 100,000 kilometers per hour or so. I don't know, per hour or per minute. Really doesn't make much difference for me, because these numbers are all humongous numbers. You imagine a black hole the size of millions of times of our sun, without making any noise, silently moving at terrific speed across a galaxy. They have discovered that. So the point is, we don't know where these things came from. We don't know anything about them. So for example, there is a branch of physics called string theory and cosmology, okay, where people say that, okay, I believe that this kind of thing may happen. And then you say that I believe, and of course they don't believe just like that. They have some inspiration. See, they have got some data, then they have got some math. They put that together and say that this is how it's behaving. So let me postulate that it will behave like this. They postulate something, and then they write out a theory, and then they say that, if this theory is true, then it should behave like this. And then it may take years, decades, unless you have experiments which confirm that it really behaves like that. You don't know. So that is the other approach I am saying. objects that you cannot see, you cannot observe, you cannot measure, you start with a theory of your own. Using some information, you postulate a theory. And from that theory, you create, you say that, okay, if this theory is correct, this is what is going to happen. Einstein, for example, said that, all motion is straight and all space is curved. Okay, and it's a fantastic statement. That's because, you see, he predicted that, stars behind the sun, their light will bend, and you will be able to see the light of the stars. And Rutherford, I think, went on a ship to measure that. Okay, he sailed on a ship to measure that, I believe. And so what is it that Einstein is saying? See, the point is the photon from the distant star is traveling only in a straight line. The problem is that space is curved. Why space is curved is because the curvature is due to gravity. So what happens is space-time has a curvature. The curvature is affected deeply because of gravity. When there are massive objects like the sun. Okay, so that was Einstein's theory, and it was verified. Okay, so the model, and Einstein, of course, said that there are going to be, these these gravity waves, which were discovered just a few years ago. Okay, they're very hard to record. And where did all that come from? You see, Einstein was using intuition and theory, and then people did experiments and they are able to confirm it. Even Chandrasekhar, derived the Chandrasekhar limit. Okay, yeah, I think cell phones are, you should put your cell phones in, mobiles in off, or at least silent. So I can understand this generation is surrounded by all kinds of gadgets. But then, there's a problem with this. The problem is your main gadget may be missing. Because you are only looking at other gadgets, this gadget may stop working. So, you should restrict those other gadgets. All right. Otherwise, you will become so there was some post on WhatsApp. There is a monkey looking at, there's a monkey hearing, there's another monkey looking at it, there's another monkey talking. Okay. As against hear no evil, see no evil, speak no evil. And the caption was WhatsApp, not WhatsApp. WHATSAPE. So we've all become apes, okay, with these gadgets. So you shouldn't end up like that. But this is you should try to know how to manage your gadget time. So incidentally, the way I do it is, once when I get up in the morning and take coffee, I look at it. Then once before I go to office, every time about a couple of minutes. Then once at lunch, once at evening tea time, and once at dinner. Every time not more than 2 to 3 minutes, maximum 5 minutes. That's it. That's already about 25 minutes. Okay, but that's it. Beyond that, I will just not look at it. Okay, and I tell many people that if there is anything important, don't send it by WhatsApp, send it by email. Okay, because I spend more time looking at email than at WhatsApp. So you should learn to manage your gadget time. Anyway, let's get back. So you see, the moral of the story is that many things, Chandrasekhar limit. Chandrasekhar was given the Nobel Prize for discovering the Chandrasekhar limit. That is the idea. That is a limit that will decide whether a star towards the fag end will become a white dwarf or it will become a supernova, right? So but that was completely theoretical. It was theoretical. Okay. Similarly, I think if you go back and look at many things, for example, antimatter positrons were only thought of theoretically before they were discovered. So what I want to tell you is the theoretical approach is very powerful. Sometimes mathematics can predict in advance what's going to happen. It may take years. Gravity waves took years to discover. Because the point is you need that much of, you need that much of technology. For example, Higgs boson. You need Large Hadron Collider. You need that's very expensive, project. So, but the point is that shouldn't stop theoreticians from saying that this is what might happen. Okay, so that is another approach. So you can start where you don't know. You can start with the theory. You can postulate and you can create. Okay, this is what I believe. This is what is going to happen. and you can keep it. Okay, that is also an approach. Okay, now you see, so let me get back to this. See, the point is all laws are differential equations, but the question is, where does this leave us? This leaves us with the question. The question is, what are the relations with respect to the variables themselves. I mean, what I mean is the variables. By the variables, I mean those whose derivatives appear. Okay, so you see, this is exactly what she was asking. Okay, so you have f is ma, so you get, so basically you are having f is equal to m, dv by dt. Then the question is, what is v of t? Or you can also write it as m d squared s by dt squared, and then you can ask what is s of t. So you see, there is this thing from the the laws are differential equations. Differential equations involve derivatives of variables, but I want formulas for the variables themselves. Okay, and so you have to, from the differential equation, you have to remove the derivatives. You have to undo the derivatives, and undoing the derivatives is essentially integration. So you have to, so you do what is called as integrating a differential equation. So the answer to this is integrate the differential equation. Okay, and this is exactly what you said, namely, dv by dt is equal to f mod m. Okay, and then you can write v. So v. So let me put vt minus. So if you write it in, let me write it in differential form. Dv is equal to f by m dt. Okay, and then you write. So you will get, you integrate from t0 to t1. dv is equal to integral f by m. Pardon me. No, what I mean is, yeah, you're right. So I'm the reason I am writing this is because everything is a function of time. Yeah, in the sense of time. But there is, you're right. Actually, I should, more correctly, I should write this as v0 to v1 dv. Okay, where v0 is just v of t0 and v1 is v of t1. And here what I mean is that this is actually d of vt here, right? And then of course I'll get f by m t0 minus, so here also it's t0 to t1. I'll get t1 minus t0, and you get so you'll get v0. So I'll just put if you want to make this as a function, you just make the upper one as t. Okay, then I will get here I'll get v, I'll just put it as v, and then I'll get v minus v0 is equal to f by m into t minus t0. Okay, you get something else. So moral of the story is, this is your v of t. Okay, of course f by m is of course a. If it had it be a, and by the way, I am assuming f and m are constant, a is constant, so I am pulling this out of the equation. So this is a case of constant acceleration. Okay, and of course this is what? This is your v is equal to u plus at. If you put t0 equal to 0 and v0 is equal to u, this is your good old v is equal to u plus at. Right, after all, right? And you do one more integration, but again, this v is still not very satisfying because there is still a derivative sitting there. V is actually just ds of t by dt. So you do one more integration, then you will get s of t is equal to ut plus half at squared. Right? You know this. So to sum up, laws of nature are differential equations. In the differential equations, there are certain variables which are not directly involved, but their derivatives are involved. You want the formulas, you want the expressions for the variables themselves. So you have to remove the derivatives. So you have to integrate the differential equation. That means you have to solve differential equations. Okay. So this is motivation for why you should study differential equations. So in principle, therefore, you see that you do anything with nature, there's a differential equation hiding somewhere. Okay, and you need to find the differential equation. You need to solve it, and then and so here is the important. The important thing is you get these pakka formulas. So you get this pakka expression. That is where you have succeeded in the theory. Because I want to know, I want to predict at any time what is velocity. I want to predict at any time what is the displacement. I cannot do that unless I have formula for velocity. I cannot predict what is the velocity at time t. Unless I have formula for displacement, I cannot predict what is the displacement at time t. Okay. So what happens in real life is that, for example, if there is if ISRO has launched a rocket and it's moving, okay, so what is happening is that there is a telemetry station which is continuously, it is tracking the position of the rocket, and that position of the rocket is being fed into a system which is both which involves many things, okay, but essentially what that system is doing is it is taking those data points of the movement of the rocket and its velocity, and it is creating a differential equation. It's solving that differential equation and giving you the trajectory, and it's plotting the trajectory, and that way they have they have a fixed trajectory which they want the rocket to go, because the rocket has to go in a certain way, and then it has to go into an orbit and then release a satellite or whatever it is. So there is a particular trajectory. That is how that is a fixed trajectory that they already have. Okay, there is this trajectory that it is actually tracing out. That is being that involves everything at one go. You are getting all the information instantaneously. You are fitting it into a differential equation. You are solving the differential equation, and then you are drawing the solution. And then the question is whether the trajectory that it is following, is it the same as the original trajectory? Otherwise, you make corrections. So the systems have, if there is they know how to make the corrections so that the trajectory can be restored. Okay. So the moral of the story is that this is happening in real time. The same kind of thing happens with, for example, tracking missiles, or so many other things. Okay. So moral of the story is that. So what I want to say is, why do you want this theory? By theory, I mean, why do you want a formula? Because you want a formula that will work at for any value. Okay, and to get the variable itself, the formula for the variable itself, that is the aim. Then you have solved that law. Okay, the law is a differential equation. Solving it gives you the values of the variables as functions. That amounts to integrating the derivatives. Okay, so I think that. So again, let me repeat. If you want to study nature, you have no way. You have to study differential equations. That's the import of everything. Okay, and this is very, very deep. For example, you take stock markets, you take drug delivery in the body. You take anything. There's always a differential equation working behind. So you need to get to you must find the differential equation, you must solve it, so that you know what happens at any given point or situation. Okay, all right. So that is enough motivation for this. Now I'll go on to giving you some idea about the theoretical aspect of it. There are there are a lot of things in nature that have inspired science. I mean, have inspired mathematics, especially, and physics. Especially the most important things that one comes across, and you will also learn it when you join college. You study electrostatics, you study heat, you study waves. Okay, so there are these three fundamental equations, and trying to study these equations and their solutions. Okay, how to solve them, and probably you can. There are also online graphical software where you can even put in the boundary conditions, and you can see the waves or the heat distribution, etc. Okay, so it's very, very interesting. So there are three basic things that motivation that give motivation. So prime motivations, are, see, these are from, I will take them from physics because these are the easiest and they are the most classical and they are they are pretty deep. So one is the so-called wave equation. Okay, then there's something called the heat equation, and the third thing is called the Laplace equation. Okay, and so what is the wave equation? So the wave equation is the following. So let me write this. It is so I will write out these equations so that you get an idea. U is the displacement, okay, of particle whose position is given by x, y, z at time t. So this is the position, and this is the time. Okay, so what is a wave? There is a medium. Okay, of course, if you think of electromagnetic waves, there are no medium. There need not be a medium also. Okay, but the point is, the wave is essentially, if you want to say, there is some periodic movement of particles in a medium. Okay, and of course, if it is an electromagnetic wave, you can have electric and magnetic oscillations even in vacuum. Okay, so you don't need a medium, but still you think of the magnitudes of these variations of electric and magnetic fields. Okay, so that is what is meant by displacement. Okay, so there is a region of space where the wave is moving. There are particles there's a particle at this position given by x, y, z coordinates at time t. This is the displacement. Okay, then what is a wave equation? The wave equation is going to be utt is equal to c squared u w. So I will write this as uxx plus uyy plus ucc. Okay, so I will tell you what this means. This utt means del squared by del t squared of u. Okay, so I want to tell you that this is actually this is the acceleration. See, u is the displacement. Change of displacement with respect to time, ut will be the velocity. And another change with respect to time, second derivative will be acceleration. The reason why we use del instead of d is because there is more than one independent variable. Okay, so this del means you differentiate only with respect to that particular variable, thinking that the other variables are constant. Okay, so this is what is called as partial derivatives, and that's the first thing you will learn when you go to college. Okay, but it's no big deal. It's just that you pretend that all others are constants. Only the variable you want to differentiate, you differentiate with the good old differentiation you have been doing forever and which you will do forever. Okay, so there is nothing great about it. Okay, so this is acceleration. So what the wave equation says is the acceleration is c squared times this thing is called the Laplacian. Laplacian is the sum of the second derivatives with respect to the coordinates. So uxx is, you can imagine, this is del squared by del x squared of u. By the way, this is also del by del t of del u by del t. And del u by del t is, of course, this is ut. Okay. So the second derivatives. Okay. Now you see, look at this, and what is this c? C, guess what c is? C is the velocity of the wave. C is the wave velocity. C is the wave velocity. Okay, this is the equation for a wave. Okay, in 3 dimensions. Okay, and what you must observe is that what is happening in this equation, u is the function, but the equation is only doesn't directly relate u to the variables. What it is doing is that it is relating u, second partial derivative of u with respect to time, with the second partial derivatives of u with respect to x, y, and z. You see, it's quite complicated. The question is, what is the formula for u? So this is the wave equation. So the question is, in this case, u equal to what? Find the function. That means what you have to do is, you have to remove the derivatives, and now mind you, there are 4 derivatives. There is derivative with respect to x, derivative with respect to y, derivative with respect to t, and also z. Okay, space variables x, y, z, and time variable t. There are 4 types of derivatives. They are all second order derivatives, and you have to integrate them, and you have to find a formula for that. Okay, so solving the wave equation involves this, and this is what you have to solve if you want to. Suppose you have a thin membrane, and you give, for example, the top, soft portion of the drum or a tabla, you bang it and then it starts vibrating. Okay, if you want to do that, you have to do that in 2 dimensions. The equation will be utt is equal to c squared uxx plus uyy, because this sheet is now going to be 2-dimensional. If you have a pressure wave going in the air, sound waves going in the air, then you have to use the 3-dimensional version. Okay, you have to solve that. You have to solve it. All right, and solving this is going to be it's not very difficult. What it will involve is it will involve what is called as principle of superposition. It will involve what is called as method of separation of variables, and it will also involve what is called as the method of Fourier series. Okay. So this is advanced mathematics, but believe me, it's not really advanced. Okay, if everything you look at it in an easy way, everything is very, very easy. Okay, don't get scared with all this heavy terminology. All right, it's all. I am telling you. In fact, I am teaching now a differential equations course to the very first. To the fresh batch of JEE, batch which came last August. Okay, and I think they are all Erland. The batch I am teaching is aeronautical engineering. Okay, they have their exam on next Monday, 5th. Okay, and we completed the syllabus yesterday. So I was trying to tell them, see, it's no big deal. You do only even if it is many variables, you do only one variable at a time. Differentiation, integration, that even from 11th standard. Okay, so nobody can stop you from getting centum. Okay, so that's all that is. The point is, you should know the laws. You should know how to do things. All right. So don't be scared looking at these partial derivatives and this, But what you should appreciate is that there is a nice equation like this which you have to solve. Okay, so that is the wave equation. Okay, somebody was going to ask a question. Yes.
How do you integrate partial derivatives?
Yeah, that's a good question. So the point. Yeah, so you, as you can guess, when there's differentiation, there's integration. So when there's partial differentiation, there's partial integration. So what you do is that you do a partial integration and then you use some more general theory. So that is a way of doing it. So it's the techniques have been found for over the last 200-300 years. Okay. So that's how we do these things. And people who are taking my project, I would like them to understand wave equation, heat equation. What about? So let me just tell you. I think we should have a break at some point.
Swayam Prabha, Digital India, Educated India.